Good evening. I'd like to get started, and I'd like to welcome you to the lecture of and conversation with Bill Baker, the structural engineering partner of Skidmore, Owings Merrill in Chicago. Before, however, turning over the podium to our guest, allow me to reflect for a moment on the question of design and collaborative practice today. Much has been written about this topic, and we frequently hear about the shifts in practice of architectural and engineering practice, and why the new computational tools, innovation in materials and fabrication methods have certainly softened the boundaries between these two disciplines. I would argue that that has not happened quite as systematically as one is led to believe if you read certain publications. I believe the vast majority of buildings, and I say buildings, not architecture, I think there's a difference, are still produced in established frameworks of collaboration within well-defined boundaries. These boundaries, these modes of practice, have seen relatively little change since engineering and architecture first diverged as separate disciplines and professions in the 18th century. Still, for the most interesting architectural projects today, the ones that you may read about, the published ones, the ones that are likely to change discourse, it is true, I think, that engineering has become a much more articulate and visible partner in design practice. Often, I think, the best of these two disciplines, and maybe also a trigger for their transformation, comes about through particular design challenges. This is a deeply embedded culture in our field. Just think of the design charrette, the design competition. All of these are modes that allow innovation to emerge, essentially through a moment of productive crisis. This crisis, these design challenges, may be the type that include the use of complex geometries and patterns, an issue that has received much attention over the past decade. It may also be the use of new materials and systems that force design teams to redraw disciplinary boundaries. Both issues draw in fabricators as crucial partners in this design process. In the context of tonight's lecture, I expect we will see some extreme structural challenges that create this moment of crisis. It is that crisis that forces professional leadership to emerge at a moment when the balance on this narrow path between success and failure is tipped either side, hopefully often towards success, such that innovation emerges. Bill Baker, who is joining us from the Chicago office of SOM tonight, has been at that junction of crisis many times, I believe. His success in mastering extreme challenges, such as long spans and tall buildings, have firmly established him as a structural innovator and one of the leading structural engineers in the world. He is currently professor at the University of Chicago at Illinois-Champaign and at Northwestern University. His work has won numerous awards. Some of the most recent ones include the ASCE Lifetime Award for Design and the Gold Medal from the Institution of Structural Engineers. We're very happy to have him back here tonight, so please welcome Bill Baker.
I'm very pleased to be here tonight, and is this microphone working? You hear me? I think it's on. Does it work okay? Okay. All right, because I have a hard time standing still, so I'm going to wander around here. Anyway, so tonight I'm going to talk about a topic which I think is very, very important, and I'm going to be talking about it at an extreme scale. I'm talking about, the title is Studies in Scale and Topology, but it actually applies at all scales. And I'm going to talk about the tall buildings, issues, topology, and scale. I'm going to start with a very important player in this world, which is Myron Goldsmith, okay? And I urge you all to know more about Myron Goldsmith. Now, Myron was an architect, engineer. He was both the architect of record and the engineer of record for the Farnsworth House for Mies van der Rohe. And I actually have his calculations for the Farnsworth House on my laptop, if anyone wants to take a look. Anyway, he worked. He did his master's thesis with Mies van der Rohe. Here's Myron when he was a student with Mies, and he wrote. When he wrote his thesis with Mies, he always considered that to be the first piece of his professional body of work. whenever he would present his work, he'd always start with his master's thesis and say, this is the start of my career. And it was about a study of scale in tall buildings. And what's, I think, quite interesting about Myron, who was very much into elegance and proportions, as all the Mesians were, well, you'd sit in these meetings and you'd have like 20 different objects, each slightly different proportion than the one next to it. And they would study and say which was the right proportion. And so here he was trying to study this in this case, in 1953 when this was done, an 80-story building was quite tall. And studies about so he came up with various different solutions of how to study it. But he also looked at just what is the correct solution for the problem. All right? And he made this chart. This one's on bridges, okay? And what he was saying is that pick the right solution for the scale of the problem and then make it beautiful. And he didn't actually add the words make it beautiful. That was implied, okay? But don't be arbitrary. Don't select a system just because you like it, because you're willful, and apply it and try to hammer it in there to make it work. Start off, what is the right solution? Now, what's interesting about here, you could say that these are a series of species of bridges, okay? Now, nature can only create new species through evolution or mutations and the like, but man can create whole new species just by creation, by invention. Because one of the things you don't see on here is a cable-stayed bridge. In 1953, it wasn't a big player, and it wasn't part of the study. The other thing that was very important about this sometimes we call it the second Chicago school, was efficiency. People knew how many pounds per square foot were in every building. The John Hancock has 29.7 pounds per square foot of structural steel. Okay, and everyone knew that. And the World Trade Center was 34, 35, and perhaps we'll come back to that again because I think it's going to come back to carbon. Okay, the embodied carbon of structures as we go forward. Because I think we've kind of gone through a phase where if a particular owner wants to be particularly wasteful with their money and do something that's quite extravagant, well, that's their business. But if they're producing a lot of carbon to do that, maybe that's our business too. And so what I'm wondering if there's going to be more of a move towards more efficiency and more charts like this. What is the right solution for the span? And this is from his architectural master's thesis at IIT. And if you get a chance, get this book. This is a monograph by Werner Blaser, Rizzoli. And what's interesting in both his master's thesis and in this book that was done at the end of his career was an essay on scale, the effects of scale of which these things I'm referring to. And of course, he refers to Darcy Thompson, okay? And Darcy Thompson wrote this book, the first version during World War I and second version revised during World War II. And he was basically a biologist who I would say is really more an engineering mechanics person. And it was all about physics and the solutions of nature. That nature is not willful. The reason these creatures look like they do and the way, it's a reaction to their environment, to the physics of what they need to survive, which is why they are what they are and why they look the way they do. And there's a reason that a small mammal looks different from a big mammal. It's solving a different problem. And that's, and so this applies to architecture. And it can apply to a building the size of a house or a skyscraper. And I think it's important to think about, what is the appropriate solution for the scale that I'm working with, and be appropriate in that. Now, what I'm going to talk about now is tall buildings, okay? And I don't do just tall buildings. I actually do some work with Toshiko Mori, like little one-story things. I've done a few houses with Tom Pfeiffer. But today I'm going to talk about kind of things that are bigger than one story. And you can see there's a new species on the planet, okay? Because if you look at the evolution of the tall building, new systems, new ideas, new species, a little bit of refinement here, pretty flat, all of a sudden something new. What happened? How was this able to happen? How were we able to make such a giant leap? And first of all, how big is it? Well, here's a picture of it. It's a little over a half mile tall. I think a half mile is about 805 meters. So 2,717 feet, 828 meters. And just, it's hard to tell there in Dubai, how big it is. Well, if it's in Chicago, this is how big it is. Here we go, New York, downtown in the flood. The Washington Monument and the Burj Dubai together. Or, we could go to the West Coast or maybe even closer to town. It is a fairly big building, okay? And this is kind of what it looks like offshore in Dubai itself. This is a picture that was taken by one of our architects that was before it was actually even topped out. By the way, SOM, as far as those of you who don't know, we are architects and engineers in one practice. The person who sits about 10 feet from me, or maybe a little less than that, is a Harvard GSD architect graduate, Ross Weimer, one of the design partners. And, around the corner from him is another GSD graduate, another partner, Brian Lee, okay? And we all sit together, and people move all the time to sit near their teams. My structural engineering team is split into groups. There's 2 groups to be close to the architects that they're working with, and so it's all about collaboration. What is interesting, though, is let me do a little diversion here. Chicago was traditionally an integrated practice city. Everyone, Daniel Burnham and all these people, they all worked at one time for Jennings, William LeBaron Jennings, and everyone says he was really an engineer, okay? And then Louis Sullivan, the famous architect. Well, his practice was Adler and Sullivan. Well, Adler was an engineer, and Sullivan was the architect. And when Frank Lloyd Wright came to work in the office at Adler and Sullivan, sorry about that. When he came to work at the office, the foreman of the drafting room was an engineer, a guy from Germany named Paul Mueller, who came in there. And even Frank Lloyd Wright, when he started his own practice, he had engineers on staff that were working with him, though he worked with outside engineers also. Over time, that's kind of gone away, even in Chicago, less and less and less. But SOM in Chicago is still that. And anyhow, on the Burj, we did the architecture, the structural engineering, the mechanical, electrical, plumbing engineering, and the interiors on this one project. Okay, so let's talk about the physics of the tall building. Let's play Darcy Thompson. Okay, why do these things look like they do? Well, let's look at the nature of the problem that they're trying to react to. All right. First of all, when you look at a tall building, it's one giant beam. Okay, here's the Sears Tower. And if you look at it and you think of it, it's all these thousands of beams and columns. You can't comprehend it. You can't deal with it. And it's not really how it works. It actually acts like one giant tree or beam. Like my arm is cantilevering from my body. These are giant beams that cantilever out of the ground. And they act like beams. They deflect. They have overturning moments. They might lift up out of the ground. They can shear. So you just have to deal with shear and flexure, and you treat them like beams. I pulled this out of the archives at the office. This is an early sketch of the Sears Tower, the Willis Tower. They keep changing the names of my buildings, and I can't keep up with it. Okay. Anyway, see, my first project as a project engineer was a renovation of the Sears Tower. So I always think it was, even though I didn't work on the original design. Anyway, so here, they actually calculate the moment inertia of the entire building, as if it were a giant beam. And it steps, and then they approximate it with this primordial equivalent moment inertia. And that's pretty darn good. And that's close. That's enough to do design, okay? That's enough to start getting a handle on how this thing's going. It's not enough to go to build it, but it's enough to bring it forward, okay? And here is the base of the building, okay? Now, Faz Khan gave it the name of a bundled tube, okay? And that was kind of related to the research they were doing in the office at the time. And they found if they had a tube and it got more and more slender, it would be more and more like a pure beam. The shear deformations would be less, the flexural deformations would be more. And if you put them together, a bunch of these tubes together, they would be stronger. Guys ever see the movie Ron, the Japanese movie? Come on, it's a great movie. It's a classic. Okay, it's King Lear set in medieval Japan. Okay, see it, Ron, R-A and rent it. Okay, Netflix, great movie. Okay, anyway, so he instead of having 3 daughters like King Lear, he has 3 sons, and he takes an arrow from each of them, puts them together, and you can break 1 arrow at a time, but not the 3 together. Anyway, so that's it. So Foskon always called this the bundle tube, but to me, it's actually just one giant beam with 4 webs. And here you can see the wind's blowing. These are the forces in the columns, and each of these lines of columns in this direction acts like webs. So it's like a giant box beam. So that's one point. Tall buildings are giant beams. Second point, okay? The single most important structural parameter in a tall building is the architecture. Okay? It's quite easy to make a building, to draw a building you can't build. Okay? Or you can't make it stand up, or the forces are too big, or it's too expensive. And so you got to get the architecture and the structure have to work together. They have to be appropriate for this thing. There was a very well-meaning show in New York City a few years ago about engineering, and the title of the show is Make It Work. That's a terrible title. You shouldn't have to make it work. It should work automatically on its own. It should be a natural result that the building works because it was created together, that the engineering and the architecture was created together, so it does work. And so if you don't have the right architecture, you will not build the building, particularly in tall buildings. What is the dominant thing in a tall building? Wind. Okay? As the wind goes by an object, it'll go by in an unstable manner. If you look, if I were a building and the wind was hitting me, it'd go by on one side, and then it'd swish the other. And every time it does it, it would suck a little pressure differential, and I started swaying side to side. If a tall building were ever to fall over in a wind storm, it would fall over sideways. It would not fall over in the direction of the wind; it'd fall over sideways. And here, here's a little computer. Oops, sorry. Go back. Here's a little computer modeling of that. And here is a cloud going past the top of the Hancock in Chicago. And you can see the vortex forming in the cloud as the wind goes past the top of the building. And this is like a kid on a swing set. Every structure is an oscillator. This podium is an oscillator. This microphone is an oscillator. Okay, everything's an oscillator. And obviously a swing is an oscillator. And tall buildings are oscillators. And how does the swing work? Well, the child kicks their feet at the natural frequency of the swing, and they get going higher and higher and higher. And they get up way high, and if you as an adult tried to hold them up there, it'd be a lot of work. But they just did it by kicking their little feet. And they got up to these great heights. And that's what happens in tall buildings, is that these puffs can build on each other, and if they match the harmonics of the building, you get very, very, very large forces. And it doesn't happen just in buildings. It can happen in bridges. This is the famous Tacoma Narrows bridge failure. Okay, which way is the bridge going? Up and down. Which way is the wind blowing? It's horizontal. How's that happening? What happened is, we know more about this now, but the side of the bridge was this plate girder, this blunt edge. And as the wind would hit this edge, it would curl over the top or over the bottom. And as it did that, it would suck the bridge up, and suck it back down, suck it up, and then suck it back down until it collapsed. And it wasn't a terribly windy, it was a windy day, but it was this very steady wind in the wrong direction at the wrong speed. And it matched the harmonics of the tower, and down it came. Okay, so what we did on Burj, let me talk about that briefly, is we went in the wind tunnel. We spent about $1 million in the wind tunnel. Different shapes, okay, different models, and the building grew as we designed it. Excuse me. We started out here. We didn't even have this top on it. It was up that tall. It was 518 meters, which is 10 meters taller than the world's tallest building at the time, Taipei 101. Because our brief was to make the world's tallest building. And so 10 meters taller, that's taller than that makes the world's tallest, right? Okay. And during during the design, it grew to here. It grew from there to there. It grew 1,000 feet, 310 meters, during the design process, by controlling the wind. We actually had one that's a little bit taller that we didn't actually build, and I'll talk about that in a minute. And so we did a series of wind tunnel tests at RWDI using this balsa wood. By the way, we're trying to make our own wind tunnel in the office right now. Not to do sophisticated things, but a lot of times you don't know, is this shape better or this shape better? You know, so that you can go down to the model shop and have a bunch of different shapes. Is this better or this better? And then we'll go, when we need the real forces, we'll go to the real wind tunnel. And you can't really use computational fluid dynamics yet for that because it's not accurate. We've tried it, and you get bad results. So the partners have agreed to. We're not sure where to put it. The building's going to shut us down as soon as we turn it on. It may end up in my backyard. Anyway, but on these kind of models, you have lightweight balsa wood, or sometimes 3D printed models, sometimes styrofoam, sometimes balsa wood, and you put them there. And what you're really doing is you're measuring the shape of the building. This is a way to use it in a wind tunnel to evaluate the shape of a building. And what we found on our building is that we had essentially 6 directions. When the wind blew it into the noses, it had 3 noses, it was a Y-shaped building. The nose would act like cutwater, and the wind would just go by, and it was fairly benign. You'd form vortices, but the vortices would be downstream, and they wouldn't blow against the building. But when the wind went the other direction between 2 of the wings, the vortex would peel off there and hit the other wing. And that was a problem. Okay? And when we had our first wind tunnel test, the results were very bad. The building did not work. Okay, and so I immediately thought of the Hitchhiker's Guide to the Galaxy. If you've read the book, you'll know that the guide, which is in the title of the book, has written on bright letters on the cover of the book, "Don't panic." Okay, and it's because things go bad in life, things go bad in your professional life, your personal life, and panicking never helps. And so what we did is we started, okay, we got a problem, guys. How do we fix it? And so we started reshaping the building, okay? And we did some special climatic studies, and we looked at the directionality of the winds. And quite frankly, the building would not have gotten as tall as it finally did if we hadn't started so badly. Because if it just kind of worked, we'd probably say, well, okay, we're here, okay. But the fact that it didn't work, we had to do radical changes. And what are some of the things that we did? Well, we turned the whole building 120 degrees based on wind directions. We changed the way the setbacks happened. They used to go counterclockwise. We made them go clockwise. We added more setbacks because, here's the shape. Because every time you have a different floor plate, the wind sees a different structure. And the rate at which these vortices occur are related to the wind speed, which you cannot change, but it's related to the width of the building, which you can change, and the shape of the floor plate. You might notice that, say, if you looked in this direction, what at one point is a tail. What's this? Comes a nose. The tails become a nose. So that's all architecture. And so, working with the architects together and the wind tunnel consultants, we went through this thing and we came up. And remember the kid with the swing? Okay, had the 2 feet kicking in unison. Now the kid has about 24 different feet, and they're all going at a little bit different rate. So the swing doesn't go anywhere. Okay, and the forces went way down, and then the building went way up. Okay. In fact, so this is just related to shape only. So here's our first wind tunnel results. You can see 6 lines for the 6 directions, and this red line represents a 100-year storm. And by the time we reshaped it twice, the forces had dropped from here down to there, just by changing the architecture. Okay. Then we tune it. We tune it like a musical instrument. We play with the harmonics. And so we did a series of aeroelastic models, okay? An aeroelastic model is a model that's no longer rigid. It actually can flex in the wind. We had a metal bar in there, a brass bar that we would mill down to replicate the structural properties. and see how it would flex in the wind and what kind of aerodynamic behavior we had. And we were able to tune it so if the wind's trying to make it go this way, you make it shake that way. Because if you look at your principal periods of any object, they'll generally be orthogonal to each other. It'll vibrate this way and this way. If the wind's trying to make it go this way, that way, maybe just kind of turn the vibration modes a bit so that it shakes off axis. So tricks like that. And here's what happened. Okay, so here's the don't panic model. Okay, here's my base moments, 100%. That intermediate one, I dropped by 1/3. And the final one, which is we've grown by 300 feet, basically the Eiffel Tower. We've grown by the height of the Eiffel Tower, and we're still less than we were in the beginning. And the acceleration, which is the motion you perceive, it's still less. And we did this. Okay, we had a lot of there were a lot of people trying to do the world's tallest building, and so there was a lot of I don't know, it's like were you giving out bad information, okay? Trying to confuse the competition. So we're all using the same wind tunnels, okay? So we went into the wind tunnel with this model, which we never intended to use. And so we all got together and said, okay, it's a science experiment, okay? Let's see how good we can make this thing do. And we actually got the top of the building moving out of phase with the bottom of the building. So it would cancel itself out. And the moments actually went down from what we built. And the accelerations are way down from what we built. But it was too late to change. So, or we would have had an even taller one. Then the other thing we try to do a lot of is manage gravity. Okay? Gravity is very reliable. Okay? You can count on it. So if you're trying to resist the forces of nature, put the gravity where it helps, where it matters. And an interesting thing is, people don't realize this, but the John Hancock, which was actually originally a master's thesis at IIT, with Myron Goldsmith, who I showed you at the beginning, and Fazlur Khan, who was the engineer on the Hancock and Sears. John Hancock is a tight arch. Because the rule of the Hancock is every time a diagonal crosses a vertical, it happens at a floor line. And because of that, you can move symmetrical loads all over the face. You can put it all in the corner. You can uniformly distribute it. And so this structure is called a braced tube. Okay, so Sears Tower was a bundled tube. This is a braced tube. So by tube, what they mean is that all the columns are working, not just the corner columns like a truss. And if it's a pure truss, it's just the corner columns will be working, somewhat like the Bank of China building. But here, all the columns are working, and the reason you're able to do that is move the loads around. So, see this center column? That's the moment diagram for a point load. See that trapezoidal shape there? That's the moment diagram for 2-point loads. And so because of this, you can move the loads anywhere. Okay, now we're in this era of these very tall buildings, but it actually applies at all scale, from house up. Issues of scale. Now, let's say you wanted to do a building like the Sears Tower, and you wanted to make it bigger, or the Willis Tower, what do they call it now? Yeah, it's like if you want to make me bigger, you make me taller, I get wider, and I get thicker. And my volume would go up by, say you made me twice as tall, twice as wide, twice as thick, my volume would be 8 times as much. Which is why those elephant bones look different from the dog bones. It's a nonlinear problem. And if you were to scale up, the Sears Tower, the Willis Tower, it's just too big. You got too much floor area. You're too far from the window. The Sears Tower arguably is too far already. It's 75 feet from the core to a window. That's a long way. If you scale it up, you get. So this is a very important thing. As you try to do taller and taller buildings, how do you deal with 2 issues? The structure needs to be a certain width to be stable, but the architectural functions, the leaf spans, don't want to be too big. So this is a very ripe field for creating new topologies, new ideas, new systems. And Burj is one of those, okay? Here you have a very wide structure with a very narrow lease span. Now this is a residential building primarily. And so the distance from the corridor to the window is the same of any apartment you'd ever have, okay? And because of the nature of the structure, you have great open windows. You have, if you went to the World Trade Center, the one that went down, you had a column every meter. Every 40 inches was a column, that far apart. And the column was 20 inches wide. So your glass was only this narrow. And on this building, you know, Sears is a bit wider. But on this building, you go 30 feet between each column. And each column is only 2 foot wide. So you have 28 feet of glass for views to look out. So, you know, it's a great. And the interesting thing about this building is that it no longer scales by the cube, but by the square. If I make it twice as tall, I'll have, you know, it'll be vertically long. I have to make the legs longer, but I don't have to make them any wider. Just make them longer. Now, I got torsional issues I got to look at after, but we'll take care of it. So here I borrowed Frank Lloyd Wright's Mile High Tower image. Okay, so then there's also limits to the market capacity. Okay, if you're doing a 600-meter tower, or 800-meter tower, or a kilometer, or Frank Lloyd Wright's Mile High Tower, it's a lot of floor area. Okay, you know the Sears Tower has a lot of floor area. It's got 4.4 million square feet. 4.4. Burj has only 3. It's much taller and only has 3/4 of the space. So what does that mean? Is that you might be able to actually sell it, okay? You might be able to, the market may be able to absorb it. You might be able to afford to build it because you're not building more than the market can. And I'll show you later, Frank Lloyd Wright's building had way over, this is in metric, but it was way, those are supposed to be squares, not cubes. We'll talk about the area of that. Now, it was an interesting thing. While we were working on the Burj, everybody, you know, every few months, somebody would announce a bigger, taller building. And okay, that's fine. Good. Have at it. Have fun. Anyway, but in the end, they all got canceled. And I think a lot of them got canceled because they didn't understand scale. You know, they had like 10 million square feet. You know, just you can't sell that many square feet. You can't build. It's too expensive to build. And so, you know, you need new topologies as you go higher. Okay. Now, so here's the topology of the Burj. Now, one of the things I'd like to you know, briefly take a little side trip here. Noun plus adjective. The Sears Tower was a bundled tube. John Hancock was a braced tube. This is a buttressed core. Now, we did this on purpose. At a certain point, we decided to give what are we giving it? Let's give it a name. Why would you do that? It helps you think. Okay? Now, what I find a lot of times is that you know, people will create something, you ask them to describe it, and they just go on and on and on. Well, it's this and it's that, and you know, it's this. And apparently what drives me nuts is when you ask a structural engineer, what is the structural system, and they have to go interrogate the computer to figure out what the structural system is. They're not in control. They're technicians. Okay? But if you can create, and we didn't name this at the beginning. We named it like after it kind of like evolved into whatever it was. Okay, but we purposely gave it a name because it helps you. Let me go back. I think Mark Twain once wrote a letter to a friend, and he said my letter would have been much shorter if I had more time. Okay, when you write or whatever, to make something simple is a lot of work. And so, when you design a tall building, it's all about conflicts. You know, you get one level to work, and then you screwed up everything else in the building. Okay, you know, you got mechanical floors, you got different functions, different spaces, and so you keep working the problem up and down. You solve the problems, and you realize that you just screwed up everything else, and you solve those, and you bring them back down and up and down and up and down until you get it, and you simplify. You know, reductive process. You refine your things and refine your thinking too. think about it. It is, what is you're doing, and what is it? And how can you tell the rest of your team what it is you're doing? If you're leading a team, how can you tell them where to go if you can't describe it? Okay, and as I was saying, tall buildings are all about conflict. It helps you establish hierarchy. Not everything is important as everything else. Okay, if you got a big mechanical duct and you got a big column, the duct's got to get out of the way. Okay, it's just certain things have priority, and so this helps you describe what you're doing to your team. It helps you resolve conflicts. It helps establish hierarchy. And you can explain it to the contractor. You can explain it to the owner, what it is you're doing and how does it work. And now let me explain it to you. Okay. Basically, in the center we have this core where all the elevators are. And that's very, very important. And that acts like an axle that keeps the building from twisting. Because you can imagine a building looks like this, looks like a pinwheel, right? So, what's going to keep it from going like this? And there's been some research showing that buildings that have a tendency to twist generally have a lot more complaints. We're not quite sure why. Is it because when you look out the window, the horizon's moving? Maybe. Okay. But certainly you want something torsionally stiff. But it's too slender to go to great heights. So it needed to be stiffened. So these are just very simple buttresses. And we use just very conventional systems, just walls and slabs, just arranged in a unique manner. And so that's what this is, buttress core. And there's just the analogy of it. And here's actually the structural system of the Burj Khalifa. This is it. Okay? He's resisting a wind load here. Here's his core, and there's his buttress. Okay? So that's the structural system, the world's tallest building. Okay, let me talk about other ways that we can address this and we try to solve it. So a few years ago, we were asking ourselves, what is an optimal shape for a tall building? Okay, we don't know. So let's do some studies. Okay, so one of the things that we looked at was we used some software you get from aerospace and automobile, where topology optimization. You can imagine if you're trying to design a piece of like a oil pan for an automobile, and all you have is a piece of material, and you're just going to put dents in it. How would you dent it in order way to make it stable and the best? What's the best dent pattern? And here's like a water tank. Okay, so you have this water tank at symmetries, and you want to put a dent pattern on there that makes it stiff so it doesn't buckle. And here you go. Okay, so here's something you might think of. Here's another one. This deflects like 14, 11. Here's one you would not have thought of, but it's much better. It's a better dent pattern. So we use this software from Altair, and we set up this problem where we're going to have, to make it simple, we did and you solve this problem also using genetic algorithms. We've got the same answer with genetic algorithms. We decided to make it radially symmetry, and then we did this topographical structural optimization. We had a prescribed height, we had a prescribed enclosed volume, and a prescribed base dimension. And then we let it go and see what we came up with. And this is what we came up with. And it's quite interesting to me is that it tended to bulge out a little bit, which could make some sense, because a lot of times you don't want your lobby to be too big, and your floor area a little bit higher is more valuable than right at the ground level, so it makes some sense. But the reason it was doing that is that it was trying to increase its stiffness, its moment inertia, but it didn't care about the wind load. At the top, where the wind load is everything, it's trying to get as small as it can get in order to get rid of the wind load. So that's what we came up with. And so here's the solution. Here's how we might structure it. And you see this sometimes in other analysis. Here's a series of analysis of a cantilever. And you can see it's not unusual, though you don't see it, well, you don't see it commonly, but it's not unusual to actually have a structure that wants to get bigger before it gets smaller and is actually more efficient. You can see this one, the volume material went from 12 down to 6 just by changing the geometry. And here's another example. About a year from now, unless they uninvite me, I'm going to give a talk at MIT the Allen lecture, and I'll talk about this kind of topology stuff then, but not today. But here's a model. It's on my desk. I stopped taking it through airports because I kept on getting hassled. But it's a 3D print that we nickel plated, so it's kind of it's a beautiful object, but it's purely mathematical. Okay. So here's a proposal we did in the office: a kilometer-tall building, hollow. Okay. And so give you an idea of scale. Oops, sorry, wrong button. Okay, issue of scale, and basically on this one, we're so here's the problem. Go back to the problem. You need a structure this wide, but you don't need a lot of floor area, and you don't need great big deep floor areas. So how do you divorce those two things from each other and then bring them back together in one solution? How do you have good architectural space and good structure? Okay. Well, let's try hollow. Okay. So here's this hollow structure, and one of the things you think about this is air is pretty cheap to hold up, so it doesn't bother me to have air in the middle of the building. You got to watch that you're not picking up too much wind load, okay, through the width, but it doesn't necessarily bother me that it's empty. Of course, the architects go nuts because they keep on wanting to put something in there because it's such a grand space. Like the movie Brazil. Remember the movie Brazil, when the guys have been interrogated in the bottom of the hyperbolic paraboloid cooling tower. Remember that? Anyway, so that kind of space. So we did a series of studies. It's like a tree. It's like Johnson Wax. Okay, you've got the research tower at Johnson Wax, where you're cantilevering the floors off the thing. Maybe you have your circulation on the inside as you go around, and then you puncture it occasionally. Very, very efficient structure. Perhaps you cantilever to the inside for some of the lower spaces, both inside and outside. Once you get past the normal leaf span, and then a hotel perhaps. Now you got to figure out your elevating, which is a trick, and you got to get your walkways to work too as you go up. Now to come up with this shape, we actually use genetic algorithms. Okay, so here's generation one. It goes through all the generations, and so we had a certain amount of floor area, we had a certain height, we had a certain, and for each of these you get a certain structural efficiency. Obviously, these are pretty bad, but it would converge to a shape. It would use genetic algorithms to come up with this final shape. And then because it tapers, the wind behavior is probably good. We didn't really test it. The behavior is bad. We figured out how do you build it. You guys, the architects are like the orchestra leader, the center of the team. You can't say I don't know how to build my building. You guys got to have at least one idea, all right? Now, one of my bosses always used to tell me, every architect should have at least one idea how to build a building. And if you have one idea, there's probably more than one way to build it. But if you can't think of a way to build it, it may not be buildable, okay? And if you actually want to spend your life designing buildings that do get built, it's good to think about it. And so this thing's very tall. You worry about wind, hook time. So we were going to do a building that had a series of stages, because by the time on the Burj, those cranes had no capacity left. Their entire capacity was used up in the cable. They had almost no hook capacity left. So you have to stage it. You have to lift up by stages. And if you could maybe hoist in the middle, where you don't have wind problems, you could hoist up. You could have bigger cranes. So this is the construction idea. And the formwork technology is based on what they do for cooling towers. We talked to some cooling tower formwork contractors on this. I'm forever dragging my architectural design colleagues to talk to formwork contractors, because I can try to explain the problem, but it's better if they hear it straight from the contractor. Okay, here's another concept. I did this. That last one I did with Brian Lee, who's from GSD. This I did with Ross Weimer, who's from here also. So here's another cruciform concept, which is kind of like the Y concept of Burj. And here, so here's your problem. You need a structure of some width, but I'll do this right here. You need a structure of some width, but it's just too deep of a space. So let's keep the width and then get rid of the part that brings light into it and stuff like that. Let's create a new structure. So here's one where you have good lease spans, great views, wide structure, okay? And they actually do this at the top of the Sears, because, you know, if you look at the Sears, at the top, at the bottom, you have all 9 tubes, and about part of the way up, the corners fall off, and you have, so here's some of the upper levels of Sears, and these are really nice floors, because you have great views. You're never too far from a window, okay? And so this is the structural system. It's kind of a borrowing from Bill and Measure, what he did for this building in Indianapolis. Borrowed some ideas from him. The floor plate, you know, and so we had this huge hunks of concrete out there just to stiffen it, like the cord on a truss, okay? You know, put all your material out there where it does some good. Good structure. The behavior is good, and we actually put in slots so that the wind could leak through the building. We find this very helpful in buildings. So the wind could leak through and break up the vortex shedding. So you can see that there's a series of slots in the tower so to help bring the wind through the building to help break up the wind forces on the tower. And so here are the spaces. Here's one of the office floors. You can see you have these massive amounts of concrete, but you have almost no columns in here. So, you know, you put it out there where it does you the best good. And it goes with managing gravity and also. Another office floor plate, and it's later it's a hotel, and then an apartment near the top. And sometimes our structure is outside the skin. Why not? Okay? You know, you use the depth that's available to you. And here's how you might build it. Construction technology. Some images of it. Let's go another one. Next generation of buttress core. Okay, how much taller can you go? Now, I was talking about the Burj. The Burj had walls, slabs, and columns. Well, let's get rid of the columns. Okay, it's just walls and slabs. You know, make it even simpler because you know when you're building a tall building, if the way the technology works, you can do wall, 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 and then slab, 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 slab. So you can do a very fast cycle. But if you have columns, it slows you down because you have to do a column, slab, column, slab, column, slab. So every story you add a day to your cycle. So get rid of the columns. All right. So here we are, just walls and cantilevers. Okay. And so you know here's the bottom, the hotel, mechanical. Residential, you know, penthouse, you know, and it's one formwork system. On the Burj Khalifa, they used the same formworks for 160 times, okay, and that wasn't an accident. Then the top, we might go to the spire. We might go to concrete this time rather than steel, and just some sections to the cantilever. How do you build it? Once again, you got a stage as you go up. And the technology, so here's a Burj under construction. Look, wall, 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 no slabs at all. Boom, boom, boom. You know, you really push it up. Now the slabs are down here. They're starting to follow up as they go. Those are like vertical factories. Okay, here's another solution. Dual towers, okay? Now, so here's the problem again. This is how big here's the program and how big it really wants to be structurally, but it's too big. It's just too big. So let's split it. Let's shape it, you know. Let's play a little bit with the massing. Let's tie them back together so they act like one structure. So in this direction, so we maintain this width. So in this direction, it's wide enough to go that high. But in the other direction, it's too narrow to go that height. But then build them together so that together they go up to that height. And so here's the structural system. It's high seismic, so we have some seismic enhancements here we won't go into. But it looks like, but structurally, our idea was it's really one building with a hole in it. Okay? It's not two buildings. It's one building with a hole. It reads like two buildings. It's functional as two buildings. And each building is very efficient. Each building has the normal lease spans. You're never too far from a window. It's highly marketable. Very practical, but structurally, it's one big building. It's like the Hancock with holes in it, except it doesn't follow the rule of the Hancock quite. Yeah, it does actually, but only on half of the building. And so here's some of the forces. So you can see, like, under this earthquake load, you know, this cord is taking the load, this cord, and these on the middle are just near the neutral axis of this overall system. And so here are the floor plates. Very normal floor plates. And then what's kind of neat, one tower is residential, the other is office. So the office wants deep lease spans and lots of elevators. And the residential building wants shallow lease spans but doesn't need as much core. So what we did is we took the elevators out of the office tower, we put them in the residential core, fill it up, and then you go up and you transfer over to get to, so your express elevators, the ones that shoot you up to the sky lobbies, you go up in one tower, and then you transfer over to the other tower up to your floor. So you use the real estate. There's a symbiotic relationship here between the two towers. Well, one being residential, the other being office. And you got, you know, very, very conventional lease spans. And then we play with the shapes and the bridges. And this was with Ross Weimer, who's from here also. No, this was with Brian Lee, Sir Brian Lee. Okay, so now let's go back to Frank Lloyd Wright. Okay, he started all this thing. Okay, so his mile high tower had 528 floors. Because there's 5,280 feet in a mile, right? Every floor was 10 foot, so you use the 10-foot floor to floor. So 528 floors, plus a pinnacle, so God knows how high it was. He had 18.5 million square feet. Okay, that would have killed the Chicago real estate market for a long time, because the tower was actually called the Illinois. It was supposed to be in Lake Michigan, right outside the front door of Chicago. And, it was supposed to have 130,000 inhabitants, let's think big. But it actually had a structural plan which is somewhat tripod. It's not really a tripod. It's more like a dagger, but it is like almost like somewhere between a tripod and a cruciform. Okay, so he did have a reasonable structure. For the Skyscraper Museum in New York, I gave a lecture once on the Mile High Tower, and Frank Lloyd Wright, actually, if you study him closely, if he wasn't so arrogant, he might have been a lot more successful on the engineering front, because he actually did understand engineering to a certain degree. And he always considered himself to be an engineer. Anyway, so let's go back. So let's say we did want to do a mile high, okay? Frank Lloyd Wright's had 18 million. If you were to scale up the Sears Tower, you'd have 210 million square feet. It's a problem of scale. Even the World Trade Center, John Hancock, 260 million. 7 South Dearborn, which is a structure we did a few years ago, 80 million. Burj about 12. And some of those other schemes, I could do as much or a little as you want. I can scale the amount of built area to whatever the market can afford. Okay. Of course, this all kind of comes to the question is, so if you're going to do a tall building, you got to understand issues of scale. You should have a clear idea. Try to use rational systems. Don't be wasteful for carbon footprint and for money and for all these reasons. Use efficient systems. You got to manage wind and gravity. It's part of the process, but you can't. You just got to do it as a team. The architect can't do it alone. The engineer can't do it alone. You got to do it together. And then think about how you build it. Because everyone says time is money, but time is risk. The longer you're in the water, the more likely a shark's going to eat you. Okay, you gotta, in a building, it's like you can have financial crash, political upheaval. The longer it takes to get a building done, the more likely it is not to happen. And the next question is, why even do it? Okay, that's a good question. Right? I left that to the end here because I didn't want to derail my entire talk. Why do this? Okay. Certainly density is good and green. Okay, New York City, except for recently, is a pretty good place to be, at least from a sustainability point of view. Everyone takes mass transit. Problem today, that's good. So tall buildings are generally part of the equation. one of our urban planners was saying if the entire world's population had the density of Paris, the entire world could fit into France, okay? And the rest of the world would be empty, okay? So certainly density is a good thing. We could use less resources, less suburban sprawl, and tall buildings are generally part of that solution. But why the super tall? Well, quite frankly, you don't need a lot of them. And maybe you don't need any of them. I don't know. But, this is one expensive restaurant, okay? I mean, you do have to have dreams and inspirations, and this is the symbol of the city and the whole country, quite frankly. And functionally, it's a restaurant, okay? And so I think judiciously and, in the right time, the right place, the right moment, to do, a very, very tall tower, I think it does bring value and hope and inspiration. It speaks to a culture and a society that's optimistic and hopeful for the future. So I think that's one reason why. But it certainly is, it's a very debatable point. So with that, thank you. Okay, so.
Would you be able to answer some questions?
Sure.
Thank you very much for this wonderful lecture that I think combines, of course, the accomplishment of the work that you showed, but also the ability to explain it really well. So thank you. Any questions, thoughts?
Okay. Yes. Well, that's a real depends. This is like a rule that has been the how do you measure tall buildings? And it's something that's kind of gone nuts. When the rules were set up, the world was Miesian. People didn't do spires, for heaven's sakes. Okay, so it was the roof, basically the roof of the parapet. So for like when the rules were written, Sears Tower was it was to the roof. The antennas did not count. Okay, so then they went back and they tried to figure out, well, how tall is the Chrysler Building? How tall is the Empire State Building? Now the entire Empire State Building is kind of the rule. If you watch King Kong, okay, and he's out there swinging around, there's no antenna, right? There used to be a dirigible mooring at the top of the Empire State, okay, and that's the official height of the Empire State Building. They later put an antenna, and that doesn't count. So the rule kind of is that if it's an antenna-like thing or a flagpole, it doesn't count. But if it's integrally part of the architecture, it counts. Okay, so and so people play with that all the time. The Petronas Tower was the one that first kind of like pointed out the inconsistency, because they were like the top floor the Petronas Tower was about 20 floors less than the Sears, but the spike went slightly above the roof of Sears, so it was actually officially taller than Sears, but not. But the antenna on Sears was actually much higher than the, so it was very complicated. So that's a long answer to a short question. Yes.
In your vision, what do you think is the future of tall buildings?
Well, I think there will be a lot of tall buildings in the future. The population is what now, 7 billion people? And I can't remember the day, we're going to be at 11 billion within your lifetimes, okay? Where are they going to be? They're not farmers, okay? It was in the last few years, 50% of humanity is now in cities. And so I think people are going to be in cities, and if you're going to avoid sprawl and the like, you need to have density. You need to have, and that generally implies tall buildings, and certainly in China there's lots of tall buildings. I hope they're not, there's a lot of bad tall buildings though, like a lot more bad tall buildings than good ones. And so part of it is, there needs to be more resistance from the public of bad architecture, There needs to be the Howard Rourke Dynamite Fund, okay? Where people, is Blair came in here today? Where is he? Okay, Blair's, he's a Pulitzer Prize winning reporter for the Chicago Tribune, who's doing a Harvard thing this year. He said he was going to try to come. Anyway, so you know, these critics need to really roast people for bad buildings or developers for bad buildings, you know. And it's not, and you know, don't get me wrong, I like a really good background building. You know, one that's just well detailed, well proportioned, elegant, but quiet. That's wonderful. Let's have that. But not 40 of them that are all identical. You know, there's got to be some personality to it. And so, yeah, tall buildings are definitely here. We're you know, after 9/11, I wasn't sure if my expertise was irrelevant. Okay, I've never been busier. Okay, you know, we got that commission in 2003. It was finished in 2010. And we're doing, particularly in China, we're doing just, you know, dozens of 1,000, you know, buildings that are tall, as tall or taller than anything in the United States. You know, 300-meter towers, 1,000-feet towers all the time. You know, 500-600-meter towers, you know, often. You know. Yes. So what makes it bad tall buildings? Bad tall buildings. You know, the way they address their neighbors. You know, there are other buildings in the neighborhood, in the street. You know, that's, you know, that makes it, trying to be something it's not. I hate applied culture, you know. I think buildings should respond to the where they are in a climatic way and stuff like that, but don't put a pagoda on the top. You know, you know, because usually they're ill proportioned and they're not nicely done. You know, I think it's, but you can, I think it'd be good for somebody actually to make a list of good buildings and bad buildings. Inside our firm, we've been doing a reassessment of ourselves. What is the SOM? We call it ethos, and we come down to a building has to be one of the three, maybe all three. Simple, expressive of structure, expressive of sustainability. Okay, and then finally it has to be well crafted. And so we're purposely trying to move away from willful buildings, things that are like, you know, just doing it. You know, my ear itches, I could scratch it this way or I could scratch it this way. Okay, you know, there's a lot of buildings that scratch their ears this way. Okay, and so, you know, I think we need to move away from that. But you know, it takes designers to figure this out. Okay. Yes.
How do you avoid the stresses that affect the experience of being in very tall buildings? In either the Sears building or the World Trade Center, you were always subject to, you felt the forces of the wind, the building moved, you felt alienated, it creaked, and it just didn't feel very good to be in the building. How do you avoid that in these new buildings?
Yeah, well, it depends on the structural system. Actually, Burj is much, much quieter than Sears or Hancock or any of those buildings. And it has to do with, this building's all concrete, so it probably doesn't squeak at all, right? But, you know, and the reason Burj doesn't is because it's got a bunch of walls. You know, whereas a building that has a bunch of beams and columns, like most buildings are framed with, you know, slabs and columns or beams and columns. In the wind load, what happens, they go rhomboidal. And when they go rhomboidal, all the drywall that's buttoning into them, they have to go rhomboidal also, or you have to have proper joining around them. And then you have these head conditions, you know. Or when you have two pieces of drywall run into each other, you have to have a proper detail, because when this slab is moving relative to the slab below, and this movement could be like 3/8 of an inch, that's not uncommon, that drywall is going to lean over and it's going to run into this drywall. And then it'll squeak and green. Now, having said that, you know, the life experience in a tall building, I actually like being in a tall building, but it's you know, when you're really high, it's like awesome, but somewhat static. Okay, when you're like at the 5th or 6th floor, you're high, but you can see people and the traffic. That's kind of nice. The Hancock, you know, the views that are the most popular, the ones that sell the best, are the ones where you can look up down the lake and you can see. The ones that look straight out the lake, no one wants them because it's at night. It's like totally nothing to see. But if you look up Lakeshore Drive and you see the light change, or the storms come in, or the things, you know, there's a lot there. I have a friend who has an apartment on the 96th floor of the Trump Tower that we did. And, you know, he's always telling me pictures of like the shadow of his building on top of the cloud, you know. You know, he has to call down to find out what the weather is. But you know, like Burj is very, 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 very quiet because it's such an extreme problem. It had to be a very efficient beam. Because they're a very efficient beam, it had almost no shear deformations. It's just pure flexural. So what happens at every floor, it compresses maybe about 1/16 of an inch, or a millimeter or so, a little less than 1/16 of an inch, and expands to 60, and that's how the building deflects. But it also is very, very quiet just because of the shape. You know, we kind of killed the vortex shedding. You know, the building in the end was generally you design for drift criteria. We're way below the drift criteria. We generally design for accelerations. We're way below the acceleration criteria. And so it just came down to a strength design, basically. Okay. Yes, ma'am. Oop. You. Mark.
I have two somewhat unrelated questions. But the first is, how much taller than Burj do you think buildings will get to be in the future? And do you think there will be a need for buildings that are that tall in terms of things like convenience? You know, do you think people are going to want to live on whatever floor really, really high up? And my second question is, how does the foundation of a building like Burj compare to something like the Sears Tower in terms of efficiency and size?
Okay, the first question, people don't need these. Okay, let's be frank about that. They may want them. Okay, as far as the super tall buildings. How tall can we go? I know I could do a kilometer pretty easy. I could do a kilometer cheaper than the Burj. I know that. Maybe a mile. One of the questions is your inner ear. How much popping can you take? When you fly, they pressurize the cabins to 8,000 feet. Okay, so you take off from New York City, you go up in the atmosphere, you're quite high, but they pressurize the cabins, but they pressurize to 8,000 feet. So something around 8,000 feet, which is like a mile and a half or something. So that's maybe it's some kind of limit. I don't know. Though, let's say you did live at the top of the Burj and you had a head cold, you might have to stay at the hotel at the bottom, because if your ears aren't popping right, it could be a problem. The question about the foundation, actually, the Burj is a system that can go very, very high because as you accumulate load, you accumulate structure. And so, the wall thickness at the top of the building is 550 millimeters. Okay, at the bottom it's 650. That's all. Because rather than making the walls thicker and thicker and thicker, we just added walls. So the load kept on going. So the pressure under the foundations on Burj are quite like for a much, much shorter building because it's all spread out over. It's like when you're walking on snow with snowshoes. You put on these snowshoes so you don't sink in the snow. And so the Burj has a big snowshoe under it, big foot, so it doesn't sink into the ground. Okay. Oh, you go ahead. You choose.
Thank you. Can you talk about the economic factor and efficiency in the history of tall buildings? Are we more efficient economically when they go up and environmentally? So what are the impacts of these new buildings and how is the technology helping?
Well, I mean, the buildings are getting more and more and more efficient. Having said that, generally the energy and sustainability issues of tall buildings is not related to the buildings, it's related to the city. It's related to the density itself and transportation on those issues. Because generally, if you're going to live in a short building versus a tall building, the tall building will take more energy, but it also takes less land. Okay, so that's part of it. The Sears Tower has 100 acres of building on one city block. Okay, that's where the sustainability comes in, when the Sears Corporation moved out of the Sears Tower, the reason they did had to do with the public schools in Chicago weren't good at the time, and they wanted all their people were living out in the suburbs. So they moved out of the Sears Tower where everyone took mass transit to work, okay, because there's very little parking. And like I say, it was 100 acres of building on one city block, and they moved to Hoffman Estates or someplace where everyone drove to work, okay? And maybe their building, their four-story building took less energy as a building, but the corporation uses a lot more, you know, of the resources being out there because everyone has to drive to work. You know, do you realize that if you drive a car, your parking space is probably bigger than your office? Okay, a typical office parking space, including the driving aisle outside the stripes, is around 300 square feet. Okay, you know, 10 foot by 30, 300 square. I don't have a 300 square foot office. You know, I don't. You know, not many people do. You know, your car has more space than you do, and you had to pave it. You know, it's so. But what we're working to do is try to reduce the energy consumption of a tall building, so to try to minimize any gaps there are between that and a shorter building as far as energy. A lot of it has to do with vertical circulation. You have to elevator up and down. You have to pump your water up and down, and so. But you also have a lot of surface area. So can you capture the energy of all the sun on all that surface area? You know, are there ways to use, you know, the topology of the building to offset some of these things? But you do have the efficiency of density in a tall building. Okay? Okay, you choose.
Thank you very much. Actually, I'm much more interested in the governmental side of the building. Like when you design a building, who decides where or how the building shall be built? Do the people like in that area has like a say on what kind of shape or what kind of feeling the building gonna be constructed in that area will be? Have you met with the people around the area, talked to them?
It changes every city, okay? Well, like we did this building in Korea, which was actually quite elegant, that had a 92-story arm and then then two shorter arms. It was a Y-shaped plan also. And the neighbors complained about this, they were worried about shadows or something. And so we pushed that one down. The other two, and it looked kind of stubby. You know, we went from an elegant solution to kind of an inelegant solution because of the neighbors. You know, in China, I can't claim to understand how that system works. You know, but apparently, you know, there's a lot of times these are brownfield sites. You know, we're doing this huge project in Tianjin, which was just a giant brownfield site that the government decided to turn into a central business district. So that's, you know, driven by the government. But you know, various places, you know, in New York City you can't do anything, right? Because of the neighbors, you know, forget it. So you know, every place is different, but it's very, very changes location by location as the government. Now on the Burj, I don't know this, okay. But my suspicion is that our developer was given access to the land with some understanding that he's going to do something very special, okay? Because it was a 1 square kilometer of a former military base that he was given the right to develop by the government. So I assume that there was some understanding that he wasn't going to just turn it into a theme park or something.
I was just going to add something to your comment about Sears. I happened to be the consultant to the CEO of Sears at the time the decision was made. Mm-hmm. The decision to go to Hoffman Estates was many reasons. Mm-hmm. One of them was, in fact, the organizational disaggregation of people in the Sears Tower. Mm-hmm. As retail became more and more something that required cooperation between people, they felt that a lateral space was much better in order for the cooperation of the different departments, and that the tower, in fact, separated so many departments from each other that they could never get the kind of feel that they needed in the organization. And that was one of the major driving reasons to go out to Hoffman Estates. Totally different from...
You know, it's an interesting design question. Could you solve the problem inside the tower? You know, could you cut out in circulations and common spaces? You know, sort of we lay out office spaces completely different than we ever did before. You know, trying to make those informal contacts happen and people get together. be interesting to know. I mean, that's part of the design problem too. Is if you do have a large corporation, how can you get that interconnection, say, but within a tower rather than a suburban solution?
Yeah. One last question. I think we can just keep going. So much food for thought here. One last question. Okay. Yeah.
You mentioned the holes in the side of a skyscraper to kind of break up the vortexing.
Mm-hmm.
Did you study, or can you speak to what happens when you put a windmill in that hole or in that slot?
Yeah, we've done that. We've done a tower in Guangzhou. It's a 300-meter tower that has a series of slots, and it's probably the best possible application of this thing because the wind is almost unidirectional. And so we put some turbines in the slots, and the amount of energy you generate is pretty minimal. Okay, it tells the world that you're concerned about sustainability, but quite frankly, you don't get a lot of power, which is really too bad. But the numbers just don't seem to really. We probably spent more embodied energy making the slots than we're probably reap from the energy from the turbines. But we've tried it.
All right, thank you very much. Looking at the time, so thank you again.